Okay, so t equal 3 is here. T equal 2 is here, 2 meters, right? So it start from the length, start from here. Oh yeah, it's so it's going here, and then going back to here, and then going back to t equal 3. And after that, you will go back running through here. Okay. So if we check again, t equal 4. 4 cube this is 64232 negative 32. And yeah, so it's going here and it's going, so first, second, and then all the way here. So after several times. But what we deal with this is we are only concerned on the number. So it's going to have from 0 to 1, it's 4 meters. From 1 to 0 back to 3. From 1 to 3 is also 4 meters. And then move away 20 meters. So we need to plus the average speed. So 4 plus 4 plus 20, and then divide by 5. And we have 5.6 meters per second. So this is turning point, this is turning point. So what we deal with this one is, what I want to make sure you take some notes is, we will have this turning point, and if we take the graph, probably this will be going to have maybe like that, okay? And we'll have the turning point here, that is t equal 1, and this is t equal 3. So we have the graph. So we have some slight increasing, then decreasing, and then going to increase. Okay, and this is what we are going to analyze, to observe in the next section, in chapter 4. This is full, okay. And yeah, I think this will do, and we will have some short break, okay? And then we can continue on the chapter 4. Okay, so I'm sorry that this recording is not really going well with this trouble I have. So what we have discussed is the chapter 4, which is the introduction on application of derivatives. In the first section, we will learn about the maximum and minimum values. If you see here, if you see the graph, you will notice that we kind of can determine which one is the maximum values and the minimum values. And to differentiate between the absolute and the local, we can see on the interval. Okay, for absolute maximum and minimum, the value is depend on whether it's on the domain, which means the whole domain of the function, or just a nearby points, which is the local definitions. Okay, and then from there we can have the Axiom value theorem, which is, if we have the closed interval, then the functions in the closed interval will have the absolute maximum and also absolute minimum. Okay, and then the Axiom value theorem will result in critical numbers. And before we learn critical numbers, there are some theorem that say that in the functions, if the function has a local maximum or minimum, then f prime c will exist. Or if f prime c exists, it will result in f prime c equals 0. And we have a definition of critical numbers that the number c in the domain of f such that when we have the slope f prime c, it should be equal to 0, or we say that its tangent is horizontal, or f prime c doesn't exist, as we mentioned in this curve that we have at the c, it's not exist, okay? But that is critical numbers. Okay, now as we mentioned that if we have the critical numbers, then the critical numbers is a number c that in the domain of the function that either the f prime c is 0 or it doesn't exist, okay? So we will have some section dedicated to finding the critical numbers and how it means and how it relates to the sketching the curve or using the calculus. Okay? And for example, in a closed interval method, if you need to find the absolute maximum or minimum, then first we need to find the critical numbers. Okay, we need to find the critical numbers and find the values, and then also find the values of the function at its endpoint, which means at the x equal a or x equal b. And after we determine the critical numbers and the endpoint values, then we can determine which one is the largest and which one is the smallest, and that will be the absolute maximum and absolute minimum. So that's the maximum minimum value. Now, to begin with the core concept of the chapter 4 is basically the mean value theorem. So before the mean value theorem, okay, before the definitions, let me make clear that that it starts with the theorem which called the Rolle's theorem. So let f be a function that satisfies f is continuous on closed interval, and that function also differentiable on the same interval within the open interval. Okay, and if f of a is equal f of b, then there will be number c such that the f prime c is equal to 0, in which we can see some of the curve, like curve blue, the green and yellow. It has all these three requirements, which is continuous, differentiable, and also f of a is equal to f of b. And of course, in the middle, or in between a and b, we will see there will be a c. And the number c can be more than one. Like maybe if you see closely this yellow curve, we have two c, c1 and c2, okay, which has slope equal to 0. Okay, and from the Rolle's theorem, we can elaborate more into a precise mean value theorem. So let f be a function that satisfies that f is continuous on closed interval, f is differentiable. Oh, sorry, it should be an open interval. This should be open interval. Open interval AB. There is a number c in AB such that f prime c is equal to fb minus f of a divided by b minus a. This means that this is our slope, like I mentioned here. So this is a slope. And we already have the definitions through the limit definitions, right? Let me write here that f prime x, we can also write down the definition as x getting to a, then this is f of x minus f of a divided by x minus a. And if you see clearly that it certainly has the same value as the secant, which means the secant is the one that is cutting the curve from the first endpoint A and the final endpoint B. So it's cut. So the theorem says that the secant value here from point A to B, the green line, okay, it will be equal to sum of the slope of the curve itself. Okay. So the curve has the slope here that is determined by the red line here, which is the same slope as the green one. Okay, so which means that we can have these conditions, okay, and we can rewrite this in terms of this. Okay, and this is actually similar concept on what we have in linear approximations. Okay, so this is linear approximations. If you see clearly that this is practically, if we move this f of a to here, and this is practically similar to what we have in mean value theorem, right? So in the next few courses, we will learn on more about this mean value theorem and how we can make sense the calculus into an application for sketching the curve through this mean value theorem. Okay, so that will be our next session. So sorry again. Okay, I do apologize for some missing on recording because some malfunctions of the apps. So yeah, I hope this recording can help you to just a little bit review for chapter 4.